6, it's in 6th floor, and this is my email address. So, 2 questions. Did you receive all the material for the class, for the lecture today?
No.
Yes or no?
No, sir.
Why not?
Oh, I don't know. I'm not in charge of that department. Oh, yeah. obviously, we
Blackboard.
have that access, but on
We
the
have-
updated one, if we have an updated one.
If there is a new one,
I sent it a couple of days ago to Dr. Jimenez.
we have this one from Blackboard. If it's the same one,
I don't.
then we have it, but Hector or Dr. Jimenez haven't sent me anything else.
Okay, so who is responsible for putting the material on the blackboard?
We don't know.
You don't know. That's your school is a little bit different than. I'm sorry, he's the one? So there's nobody from the school helps you?
I guess it should be Hector, maybe.
I mean, like in
I can
medical
ask
school,
him.
we can somebody do it, and also there's an office, I can go there and ask them to, they will put it in the blackboard. And if I want, I can do it, but I never tried in your system, because your system doesn't work. Anyway, sometimes the material changes, and I make some modifications and add certain things. Anyway, let me know, okay, so in case if you're missing something. So the coordinator's responsibility is there. So I did coordinate one time ago, so I know. That time the blackboard didn't exist. But we have been very at the top of everything, because basically the communication is very important. If there is no communication, if the communication breaks down, nothing moves. And then somebody's going to pay the price. And in most cases, probably the students, right?
Yeah.
Because we have a very small voice.
I think at this point, it's easier if you just send it to her. She's the representative of the student.
All right, so that we can make an arrangement of that. But at the same time, if it's a student representative, you should be in touch with the coordinator every day, every minute, every time. Do we have any update? You have to push that, you know. Okay, so that's yours, because this is your responsibility, your idea to do that. Because many times people are involved or busy in different things, might forgetting and things like that, or part of something, could be ignoring things, right? But that's, it's an honest error, it's acceptable. And if it is made intentionally, which is not acceptable, right? Because you guys will not be at the same speed as you'll be talking about. All right, so this is a biochemistry, but your biochemistry class is obviously not integrated with any other courses. It's just freestanding biochemistry course, right? So this biochemistry course sometimes has become a little bit of dry because the biochemistry is the same. Whatever the language is used, from wherever you teach, material remains the same. Carbohydrate remains the carbohydrate. It doesn't become amino acid, or amino acid doesn't become carbohydrate. Well, there's a possibility, yes, there are processes which we can make carbohydrates out of amino acids too. But the basic structure has already been done for a long time ago. When you make a roadmap and you try to fill it up inside, you know how this molecule not only is being built, how it's regulated, and what exactly we need to have this. So I'll be giving you some ideas about the structures, mostly related to that, because it's all chemistry. No matter what you do, study the biology, whether it's in the oral cavity, or it's as in brain, or in heart or kidney, anywhere, this biochemistry remains the same. And the metabolism of carbohydrates more or less remains the same, except for certain cells will not be doing the complete job, or some tissues like the liver has an enormous amount of work to do, because that basically supplies the glucose to enter the body, through the blood system. And so that's why whenever we are eating or digest, we have to digest our food. And the digestion starts as soon as you start eating. It's not that it has to go down to your stomach, it doesn't. That's why we have this oral cavity, and also our teeth, it has to grind it, and so that we can swallow it, and it goes down through the esophagus, and then goes to the stomach. But again, it starts, in terms of the carbohydrate, it starts breaking down right in your mouth. It's not a complete one, but it will make it bits and pieces, like a smaller molecule. If you have a small molecule, it's not a problem. If you have a big molecule, you have a problem. Question is, big molecule has to be broken down. Our system is such, we can eat many complex molecules, the protein, carbohydrates, lipids, and all of those. But it has to be broken down to its units, that are the metabolic, the body rebuilds. Because the question is, we cannot absorb all these big molecules. The cell cannot absorb. Cell does not have all the machineries to do it. Okay? So that's why it has to be broken down into a single molecule or simple molecules, and then it will rebuild. Basically, it depends on our need. The need varies. It's every second, every minute, our need will be changing depending upon that what type of. And right now in the classroom, are paying attention to the lectures which I'll be talking about, right? So, and you'll be thinking at the same time, so you'll have a lot of mental activity rather than a lot of physical activities, you know, running wild, something like that. So that's why, in order to provide, it's basically connected with the energy process. It's like we have to maintain the energy. So who is responsible for providing the energy? And how efficiently it can do it. So that's why different pathways have been identified and have been studied, and they're highly regulated. Okay? So in the first part, I've divided this lecture into two parts. One is the part 1 and part 2. Part 1 gives you the orientation, kind of what are the sugar molecules looks like to us. The chemistry part I'm talking about. Yeah, if you think that you are adding some sugar, whether it's the white sugar, the brown sugar, everything, for the coffee, you know you're adding sugar. But what do they have? Okay? So what is the chemical nature of the sugar? Okay? So if you know this, then you know that how it will be broken down in the system, and how each one of them will be contributing to our need for our body. So like say, for example, sugar, what we talk about, the sucrose, right? It's the glucose and as fructose, right? There are two different molecules. The names suggest the two names. The two sugars, they're all have the similar chemical formula, you can say. But with the name, they're suggesting that they're different sugars, but they will be needs to be handled differently. And why they've been created like that, and based on that, now the question comes always to my mind. I never had the answer yet. It's from the evolution standpoint, that whether the sugars came first or the enzymes came first. Because the enzymes, they're the ones who are going to handle it. So if you don't convert one sugar to the other sugar, like when you study the glucose metabolism, glucose to fructose, glucose 6-phosphate, fructose 6-phosphate, and then fructose 1,6-bisphosphate, the enzyme which will be responsible for breaking down the fructose to 6-carbon compound to 2 molecules of 3-carbon compounds, it will break it down exactly at the same place, at a half, 50-50, so that both parts would be used. Because there's again, fructose is a keto sugar and glucose is an aldo sugar. That conversion is necessary for the enzyme to be able to break it down into 2 equal halves, so 3 carbon each. If it doesn't, then it will be a disproportionate breakdown. The other part will be wasted, and we don't want to do that. So that's our body has not. So in a sense, the Mother Nature has created in such a way so that we can get as much energy, which is stored, the chemical energy stored in the glucose molecule, the carbohydrate molecule, we can extract it. Not necessarily in the biological system, it's never been 100%, right? So it's always there is some wastage there. But again, it's 80%, 90%. It's very close to 100%. Right? Okay, so you already have the objectives, right? You have? No, you don't. Even though everybody has not downloaded that information, or you don't have the.
Yeah, there's another document here.
Yeah, there will be 2-part lectures, the PDF files, and also the objectives supposed to be the PDF file, right? So that will be the PDF document. So no signal well. Slow? Oh, sorry. Okay, the one other thing I need to do with my phone is the airport mode. Okay, so, okay, the objectives, these are the course objectives. So I have also, this is the first part, which I'm going to talk about now, and the second part, there are separate sets of objectives. So these are the ones which are basically, you're trying to recognize that what are the different sugars. The D and L sugars, it has a 3 to 6 carbon compound atoms. What is meant by the monosaccharide, disaccharide, oligosaccharides, and polysaccharides? What are the difference? What the definitions are? What do you mean by epimer or anomer or the stereoisomers? Okay. Then you have how do you define the conformation and the configuration of sugars? Because when you study or start reading your books, you will find all these things coming up. So the question is, what are those? Okay. Then the glycosidic linkages, when the sugars are joined together, like amino acids is with the peptide bond, like peptide linkage. Sugars, when they join together, they call it glycosidic linkage. So we'll talk about that. Then we're talking about some polysaccharides, which means they're made up of, it's interesting enough, these are all made up of the single sugar, but they have different names. They're all made up of glucose. Then you can say the glycogen, then you have cellulose, and they have starch. What are the differences? Why do you call them separately? Now, interesting thing enough, that the glycogen, the animal body can make glycogen. We can, human system, we cannot make cellulose. Neither we can digest cellulose. We don't make starch, but we can digest starch. Okay? So this gives you some exciting information, because this is, after all, metabolism is highly challenging. Because since, as I said, it changes every time. So it's not like a gene expression, which takes time even to synthesize the protein, right? So, but here, environmental factors can change your metabolic status at any time and point. And then we will be talking about the glycosaminoglycans and proteoglycans. These are homopolysaccharides, they are heteropolysaccharides, so there are different functions. So basically, now if you look into the perception about the carbohydrates, now if you ask any of those group of people, that they will have a different, not the information, they will define it according to their needs. So that if it's an Weight Watchers or some athletics, somebody is talking about them, that basically they'll be looking into how we can maintain the optimal amount of the nutrients, so that I can, if I'm a sprinter, which has to run fast, and if I'm a marathon runner, I have to hold on to my energy for a long time so that I can run for hours, right? Several hours. So they have a low-calorie, fiber diet, foods, and latest is fashionable diets. We'll talk about that for the Weight Watchers. Now, physicians, it's included everyone. It's not the MDs or the DMDs are also included, right? So it's in one word. The physicians will be thinking of the medical conditions related to that. And so that means, you have a patient, when you'll be examining, somebody will come up with some different type of diseases like diabetes and others. And some rare lysosomal enzyme deficiencies. Some people have cardiovascular diseases, glycogen storage disorders, and perhaps nutrition. The cell biologists, they'll be mostly focusing on the protein glycosylation markers or intracellular protein trafficking or the protein degradation. When the proteins are made, then we have a half-life. It's not like once you made one day and it stays there till we die. No, it not happens, because they're constantly being made and destroyed. So as soon as this need is done, it'll throw it out, because the cell has a limited space. It cannot expand it to beyond certain level. And there's another new science that's emerging. It's been emerging for quite some time. So the name has been changing. So it's a glycoscience, basically, is now, because there's the biology and the physical component together. The glycomics and the biology together, now they have renamed it called the glycoscience. So if they ask you, they will ask that they will picture the complicated sugar chain structures and how they are being built. Because when you are building amino acids, there is a genetic code. You'll see that when you're adding the polysaccharides or homopolysaccharides or heteropolysaccharides, the sugars are being added how they are being added. There is no code for sugars. So there is a glycome, what we call it, it's a hidden code. Nobody has discovered it, how the sequence will maintain, how it's being added. And cell will do it 100 million times without making a mistake. If they will make a mistake, then you know you have a problem. Or it will make a mistake if there's a problem somewhere else. Okay? So they will be mostly dictated by the glycosyl transferases, the biosynthetic pathway, and the search for specific physiological functions. And if you have a deficiency, it will lead to genetic disorders, called the congenital disorders of glycosylation and even in cancer. The application of glycobiology now is huge and humongous because some expression of some glycans will make the cancer to proliferate. Some of them probably regress. So if you can come up with this window of opportunity, then you probably can build up new therapeutics. It's called the glycotherapeutics in that respect. Okay. Okay, so let's say most of the time we're going to focus mostly on the glucose because I think that is the, we consume enormous amount of glucose. Okay, our body needs 120 grams of glucose a day. And it probably can store it 160 grams. So that's why after every 24 hours, every now and then we feel hungry because the reserve goes down, it sets a signal, you have to go and eat something. So that the central part, if you say the glucose, looking at focusing on glucose, okay, obviously as I mentioned for the dietary sources, it's been metabolized and say we are generating from the glucose, right? Or sugars we're talking about, right? The glucose is kind of a hub. And you can see that where it can be stored, that's glycogen. Now glucose, from glucose, when it's metabolized, it can make proteins with amino acids for proteins, and makes the fat components, the fat component for the fat, component for the porphyrin or the heme biosynthesis. Obviously it will be metabolized, that's what we're focusing on, major part of that. The extraction of energy will be from the ATP, NADH, FADH2, and so on. But those are, you probably heard some of the oxidative phosphorylation part you must have discussed, right? Previous lectures. Some of those things you already know. Then there are the components for new glucose synthesis, which is called the gluconeogenesis. This is, you can say, the glycolysis, aerobic and aerobic glycolysis. This is the gluconeogenesis. That part is the glycogen metabolism, breakdown and storage. And also the glucose is involved in making nucleic acids, which is ribose, deoxyribose, which is the components of DNA and RNA. And the sugar nucleotides of protein or lipid modifications. And they also convert conversion to sugars. So the glucose can be converted to so many different sugars. And they are not doing it just to keep us, say that not keeping us occupied, but also it is a genuine reason for doing this. So the basic structure, for this one, as I said, as soon as you start eating, you have to whether it's starch, which just means, it's rice, or bread, or something like that. Okay, or you have lactose, which is like milk products, dairy products, and that, or sucrose when you're adding it into your glucose, in your coffee, right? Or I'm sorry, is anybody here? Somebody saying something? So they as soon as it enters the oral cavity has something. It has amylase, but the oral cavity is not dry. It's moist. It has many things. Amylase is one of them. There's many proteins, glycoproteins, mucins, and so on. Because if it is dry, then you know you have problems. You have come across probably some of these patients. Some individuals, they have what's called a dry mouth syndrome. They cannot swallow, and so then you have to go back and provide them some remedy to that. So the amylase is one of those salivary amylase that will start breaking down to these big molecules and making into some smaller molecules. Like, can say that as I say that it will not completely digest it to a unit form. Yeah, so to a single unit like the glucose, it comes from the starch, but at least like a maltose and all of those that di, tri, tetraoligosaccharides, Yeah, but the amylase will stop, whatever it will do, but the food is not going to stay, it's going to go down, right? And so, as soon as it hits the stomach, amylase will cease to function. Why? Acid of the stomach, the low pH will kill the enzyme. As you know, that is any protein probably will be destroyed in that. So what happens? Then we will not be able to digest the sugars anymore? No? Then how are we going to get our sugars back?
Yeah.
That's the fallacy, right? So
There is another enzyme that convert the pH como que combate, it fights the acidity of the stomach, so it can go down the small intestine.
Okay, and then what happens?
You go to the duodenum.
I'm sorry?
That's when you go to the duodenum, and
I cannot hear it.
that's when the part that you go to the duodenum and you get the extraction of lipids. It was.
No, I'm talking the lipids, right? No, I'm talking the protein. I'm
Protein,
talking the
so-
carbohydrates, sorry, not doing the protein. So anyway, yeah, because the stomach pH will be, better than the pancreas systems in bicarbonate that will neutralize some of them. But there will be another amylase which is coming out of the pancreas. This is the second amylase which will be taking care of and degrading them further into smaller molecules, and then you have specific enzymes like maltase or sucrase or lactase, giving the glucose molecules, maltose is the glucose, sucrose is glucose and fructose, one molecule each, and lactose is glucose and galactose. So that they all being released, I mean, in a monomeric form, and through the portal circulation that the body will distribute, it goes into the blood and then goes to everyone, every system, so possible. So now every cells will pick them up, those who have the transport capability, most of them they have, and enter into the cell, and they will be metabolized according to the machinery the cell has. All right? And some of them will work when you have an oxygen present, aerobic conditions. Some cells will work as an anaerobic condition. The red blood cells, they don't have mitochondria, so obviously they cannot extract glucose all the way to burn it to all the CO2 and carbon dioxide. So the glucose is metabolized, you get the same number of molecules or atoms back. So the glucose or any sugar, carbohydrate, this has a general empirical formula. It's called the CH2ON. Does it work in the any? No?
What do you mean?
Yeah.
There.
The provide us all the fancy board, right? But they don't put us the erasers. People, they'll say, well, the students take it home. I said, I don't know what they're going to do it. I don't know. Take it. Find out. Okay, I think. But now you cannot even open the door after sitting down, right? It's locked. Since when? No, I know it happened recently. It was not there a year ago. I don't know how many months before, if we're counting back, that when they have installed that logging system. Because I'm going to go into a little story that I just, somewhere or other, I just passing by through this corridor. And one of your faculty members of the dental school, Dr. Elias, Augusto Elias, you probably know him or not by name. He was not in the 224. He was standing near the door and trying to open the door. And I looked at it, I said, what happened? How did you manage to lock yourself in? And I tried to open it, it won't open. And it was late, it was like a 5:30 or close to 6 in the evening. So if you would have passed by, you would have been there in that room for a whole night. So I had the phone number of the security, chief of the security. I called Mr. Figueroa. I said, Mr. Figueroa, there is something here happening. I don't know what happened. Would you come? Because I don't have the key. Can you open the door for this professor? And he came. He said, well, we changed it. I said, where's the key? He said, well, there's no key. It's a card or something in the code. So that's what I'm saying. So they changed this. It happens, but they don't tell anybody, right? They don't give the code. So how do you get out? But you should be able to get out from either pressing a button or something, or what? So I have got no idea what they had it inside. So anyway, so he could not come out. So what I'm saying, that there's always a communication problem. So we have to maintain our communication wide and open. I have got no problem with that. Anyway, the carbohydrate has this empirical formula of CH2O and its N. The number of N's depends upon how many carbon, how many oxygen, and how many oxygen you have. Minimum would say the number would be 3. C3H6O3. And the glucose, it's a 6-carbon compound. So it has the N is 6, and it is 6, C6H12O6. Now, if you take this empirical formula, CH2O, in a chemical terms, how to define this molecule? How many had chemistry before? Undergrad? Not everyone? Everyone? Okay, good. Okay, so how do we define this one? Now, if you dissect this part, these two parts, carbon and water, how do you define it? It's a hydration. It's a hydrate of carbon. Does that make sense? That's what it is. And so that, and you can say that sugar molecules is a hydrate of carbon, but it varies. So that's what we're going to talk about. That glucose has 6, I just given an example, but the minimum, we have the shortest one is the carbon 3. There are 3 carbon atoms with that. Okay, so now it's going to be reabsorbed into the system, and we're going to distribute it all over the body. And then we'll study the glycolysis. Somebody will pick it up, and they'll try to explain each one of them, how each of the sugars are being metabolized. And you are extracting energy, or you are making some of the products out of that, make something else. Okay, so the nomenclature, we have monosaccharides, the classification, configuration, conformation we're going to talk about, which means single sugar. Disaccharides means 2 sugars, tri is 3, tetra is 4, penta, and after that becomes alcohol. Then we have polysaccharides, they're huge. In terms of molecular weight, over the millions. So polysaccharides, and we have homopolysaccharides, means made up of the same sugars at the n number of times, or x number of times. And of the heteropolysaccharides. The example of the homopolysaccharides is they could be structural, like the heteropolysaccharide is cellulose, or they could be storage. It's a homopolysaccharide, which would be starch or glycogen. Or this heteropolysaccharide could have a functional consequences, which we'll discuss a little bit later, with glycoproteins, glycosaminoglycans, and glycolipids. I'll focus these 2 areas, but not that one. Then we have a glycoconjugates, which means the sugars when they're attached to lipid, or they are also the proteoglycans. This is the mixture of a heteropolysaccharide attached to a protein core. So that's gives the proteoglycans. These are all present in our in animal systems, in the humans. Peptidoglycan you will find them in bacteria. So you know you have to deal with them. Sometimes you have a lot of infection, right? So we ought to have to treat with all kinds of antibiotics, right? So that you know to kill the bacteria, and then you have glycoproteins. So, and all this therapeutics, whatever it is, starting from infectious diseases to cancer, they all try to protect, some rather to kill the cells. Whether to kill the bacterial cells or to kill the cancer cells, right? So the philosophy more or less remains the same. But the question is how to get to that point, okay? Without hurting the normal cells and normal tissues. That's the biggest challenge we have. Okay, the monosaccharides. Here's the monosaccharides. It says a lot of things, right? And I want many things from you fast, but not one thing. That don't try to memorize. Don't try to memorize. Try to understand. Because memorization means within the next minute you will forget. And I'm trying to give as much logic as possible so that it sticks to your mind. But when you open your chapters or your book, you will then realize. By the way, which book do you follow? Written book? Yes, no? That's what edition? The 5th edition? The latest one is very good. It's well improved. It's improved a lot in that respect. I can tell you this. So, sorry? But you can go to any book. You can go to Devlin, you can go to Lieberman, Marx, and Pete. I don't know much about the Montgomery, so there are many other biochemistry books available for that. The Devlin is I would say, Bellinger also something we use. That's the most disgusting book in a sense. It's not disorganized very much. So my favorite is Devlin because it's this thick. That is well chapters wide, and it's a flow of the language of English. It's much easier to follow than many other books.
What was the name of that?
It's a textbook of biochemistry by Devlin, Thomas Devlin. Yeah, I can send you that. You can send me one of the contact information. Okay. Yeah, because I was thought of making this with a list, but unfortunately my computer was not connected to internet for some reason. I tried, but it failed. After that, I said, okay, I'll keep that later. Okay, so the monosaccharides have been classified as aldose or ketones, depending on what group you have. It's the aldehyde group, and you have got keto sugars or aldose sugars. Then they may ring structures, and they can form a cyclic structure. So then there will be that. Then when this rearrangement takes place, the carbon 1 becomes the anomeric carbon. Okay, it will have a reactive hydroxyl group. It is not attached to another molecule, and the sugar is classified. This one is the reducing sugar because of the presence of aldehyde group. I mean, both of them, ketones and aldose. It's the keto sugars, the 2 carbon group. Then they can isomerize, can be compared with other monosaccharides and classified as their isomers if they have the same number of carbon and hydroxyl and hydrogen. It may have the same chemical formula. The reactive hydroxyl group, is covalently attached to another molecule, then it could be disaccharide, or it could be classified to the amino acids. The protein is the N-glycosidic linkage, or glycosidic linkage when 2 glucose or 2 sugar molecules attached together. If attached to this group, the NH2 group or the hydroxyl group of the amino acids. So here you go, the same chemical formula. You're extending it. For example, you have epimers, and then you have enantiomers. What's the difference? Unfortunately, the undergraduate chemistry, whether it's in a chemistry major or a biology major, they're always focusing on the genetics and things, but nothing in metabolism, right? And not regarding in chemistry. So the epimers and enantiomers is important because they're 2 sugars. They may have the same similar structure, but they are called epimers there because they have 1 subtle differences at one particular position. And enantiomers is the mirror images, which you talk about. They form the chiral because they have a lot of chiral centers, and some of them then will make a mirror images, and they're not superimposable. So that's where the enantiomer is coming from. The epimers is the different configuration around the specific carbon atom. Okay, so we'll give you more examples. The disaccharides, we just mentioned the sucrose, glucose, and fructose. The sucrose, lactose will be the galactose and glucose, and maltose will be glucose plus glucose. And from here, they can be oligosaccharide, and they can also be linked to polysaccharides. They can be linear. For example, we talk about the amylose or starch. No, not starch. The amylose. The branch will be the glycogen. Okay. But they have to be linear molecules. They have to be branched because they were linear, and then some branching started taking place because to accommodate many sugar molecules. Okay, here's a simple example. The chirality here is a ball stick model. So looking into that, it has a 2 hydrogen hydroxyl aldehyde and CH2OH. 4 valences are satisfied, right? And so that you put this one in front of a mirror, you get this structure, right? That's what we call the mirror image. But you take this structure in your mind, no, not like that. You have to take it like this, not like this. If you try to superimpose what you call that, they are not superimposable. So that means they have a chirality and chiral center there. They are the, that's a mirror image of enantiomers. So now here, 2 real examples, a 3 carbon compound of sugar. It's a glyceraldehyde. It has the one, CHO group or CHOH and CH2OH, right? And this is the structure of the glyceraldehyde. This is open ring. It's called the Fischer projections. And when the ring closes, that becomes the Howard's projection. So we'll talk about that in a moment. Now, there are little letters here, the D and L. By looking at the structure, can you define me what exactly D and L is coming from? Where are they coming from? Why have they been assigned? D and L. No?
Is it not the optical? The optical.
Is it the orientation of? Okay. Oh, okay, okay. Somebody said something.
How it looks on polarized light?
Polarized light, that's it. Yeah. Okay, I'll try, yeah, try to go to that. Yeah, because basically that you'll be able to rotate the polarized light to the right and to the left. And right stands for the dextro, and L is levo. So that's why the D and L is coming to that. But here, I mean, that's where exactly it's coming from. But for us to understand it, we're looking into, because this is going to be extremely important from now on, the presence of the hydroxyl group. This is the first hydroxyl group after the CH2OH group, right? It's after that one. This is number 1, number 2, and number 3 carbon. And the orientation of the hydroxyl group, it is on the right-hand side is dextro, is D form. This on the left-hand side is the other. So you're going to see all of the structures. Now, this is the perspective from my scale. Okay, now we're going to build the structures. Slowly we're adding 1 CHOH group, right? So now you have the 3 carbon, we have the glycerol there, right? And then it's the 4 carbon structure. So what you're adding, you have this part is fine, right? Or you already have that. We're adding 1 CHOH group. Because we are not disturbing the valence will be maintained that way. So you have 2 structures, the D-erythros and D-threos. Because there are many structures to be possible, but in biological systems, only few of them are acceptable, not necessarily all of them are there. Because it's a chemistry, you can build all of those. Then you build the 5 carbon, you're just adding 1 extra CHOH, and you can, it's a 5 carbon, the names also changes, ribose, arabinose, xylose. Arabinose you not find in the mammalian systems, you find them in plants, but these are the one which is biologically active. Those are present in the box, so we'll come across to that. And these are our 6 carbon compounds, which one of them is represented by glucose. Here's the glucose, another one is a mannose, and there's galactose. You will see them very often, these sugar molecules coming in. It doesn't mean that they don't exist. They do exist, but probably not in the mammalian system where we cannot process them.
Why is tallows still D? Has more hydroxide on the left?
It's a good question. There are a lot of mistakes in the books and textbooks. I'll show you one of the examples. I cannot keep on correcting each one of them. And because we don't, another thing that probably I did not pay much attention to that to point it out, because I just ignored that.
Well, it should be L, right?
It should be L because of the, yeah, exactly the truth, right? Looking at the hydroxyl groups, right? It's a D-glucose, D-mannose, here. Oh, okay. The one of the things, no, sorry. The one of the things, what if you look into that, there where the glycerol is coming into, it's here. So this is the vicinity of this. So this is because of the hydroxyl group close to the CH2O.
So you look at the one closest to that.
Yeah, right. This is the one. Okay, that's one. Okay, so now we're going to talk about the glucose, mannose, and galactose. Remember, these are all 6 carbon compounds. And we heard the word called epimers. What exactly that means. Now we are going to see that the glucose and galactose are epimers. Glucose and mannose are epimers. The mannose and galactose are not. Let's say the Y. Here is the, you put the glucose in the middle and look at the structure. That it, as I remember, the epimers mean it has to be different in one particular carbon atom. So here is look at the carbon 4. It's different, right? Now, when you compare with the glucose and mannose, these are the carbon 2. So that's why these 2 are epimers, these 2 are epimers. But if you try to compare with the mannose and galactose, they're different in 2 places. So that's why they're not considered epimers. Okay. So now moving into the keto sugars, so the aldo sugars, they are the reducing sugars. So you can, there are different tests can be used to measure that. So the three carbon compound, the keto sugar, the first one is called a dihydroxyacetone. It's a keto group. Obviously, if you take this one and you put it in the front of the mirror, how many mirror images you will get? How many mirror images you will get?
Is it done?
Huh?
Is it done? I feel like you could rotate it.
Yeah.
I mean, physically, because I mean, it only goes
There's
one
no
way.
chiral center.
There's no chiral
There is
center.
no chiral center.
Right.
Yeah, so that's
So
it.
done.
Because this is not a chiral molecule. The two valences are satisfied, taken by the oxygen. So there's no chiral center. So you cannot make, more than one molecule. So dihydroxyacetone, yeah, because the chiral centers, I'm going to tell you in a second that how many each molecule has a defined chiral center. I will take in a second. So dihydroxyacetone phosphate. The next one is erythrulose that you're adding CHOH. You're extending the trunk of the tree, I would say. And the ribulose, which is ribulose, xylulose, there are 5 carbon sugars, and the sorbose, and tagatose, and fructose, basically that should be used quite a bit on that. And you can say this is a 6 carbon compound. So these are keto sugars. And keto sugars, you have one less chiral center, right? This does not have any, but this has either n to the power, 2 to the power n, the chiral center is. So when the n is, depending on the number of n value, then you can get so many different stereoisomers in that. So here it's possible that you can get 2, because there's, even though it's a 4 carbon compound, the 3 carbon compound you cannot get any. And also name changes, glucose, galactose, mannose. When there's a keto compound, keto sugars, is ulose. You have to add this ulose. That means you know you're dealing with the keto sugars. Ribulose, xylulose, except the fructose. You don't put any ulose in it. So the fructose is there. Yeah. So in glucose molecule, that now value of n is 5. Or 4, I would say, when the open ring format. You get 16 different isomers, right? And when the ring closes, the one carbon becomes the anomeric carbon. It's also adding up one more chirality, and it goes to 5, so you get 32 different isomers. So now you know how complex it could be. So these guys will be one less because of the situation where we have this the structural differences. Now the configuration of the glucose. This is what we have been talking about, the glucose molecule like this, right? Straight chain compound. Yes, this probably exists in the straight chain compound when it's the powder. The moment it goes into solution, it does not maintain this conformation. The conformation changes. Because because this becomes because of the presence of the water, of the alcoholic group, they try to interact. Here it shows the aldehyde, and alcohol is the water and an alcohol. Think about that. So they will try to interact, forming ultimately hemiacetal and acetol. And the ketone will also do the same thing. It's called the kettle group. So while it's doing this, the ring is closed. It's forming a ring structures. So one will be like in the furan form, another is the pyran structures. What is that? It's a 6-member compound. It's the 5-member ring. All right. Now, which one makes what? And here's an example is given that out of those 4 different structural elements that have been projected, you will see only probably 2 of them will remain as a viable structure. The other 2 probably will not. The distribution, like here, this particular one is about 38%, is 62%. It's 100%, right? And this group, the less than 0.5%, and also less than 0.5% is, maybe they are totally immaterial, they are not, because they don't contribute much. One other thing I just assume, there is an anomeric configuration. Talk about the configuration is changing when the ring is being closed, because it takes out the first carbon and the 5th carbon. That's why the ring is closed. It's doing, this is the 6th one. It's there on the outside. So when it does that, it depends upon how it's closing the ring and how it is changing this the orientation of the hydrogen hydroxyl group. And that gives you the carbon 1 up. It will be more easy to understand on the next slide. That gives you the carbon 1, basically will be the anomeric carbon configuration, and it's adding another thing, alpha D. It's in the alpha form or in the beta form. So what does that mean? So if the D and L is okay, you already understood that, but you're adding in another extra burden to us, and the complexity by adding alpha and beta, because it's very important, because when it will be synthesized or degraded, the enzyme has to recognize those formulas or they're not going to touch it. Okay, here it is. There's a glucose, and it's basically removing a molecule of water, right? Forming here, this is the alpha D glucopyranose, because the pyranose is 6-membered structures, and it's also this beta D. Now, this is the first one, carbon to the anomeric carbon. It depends upon how the hydroxyl group is located in that molecule. That gives you or tells you whether it's the alpha configuration or the beta configuration. How do I remember that? Sorry? DOH, yeah. Which is what? Yeah, how the OH is oriented, exactly. If it is oriented downward, this is alpha. This is easier way to remember that. And if it is oriented upward, it's the beta form. The reason is that this is on paper we're doing it, but in reality, it's a, I mean, this is all what is saying on paper, but this is a 3-dimensional structure. If you look at it, this part is toward us, and that on the back of the screen, and that's what it happens. So here the structure is a pyron structure, furan structure, the alpha-D-glucopyranose and beta-D-glucopyranose, and here's a fructose, even though it has 6 sugars, but it prefers to have a furan type of structures. Now, this is all the chemistry has been done. If you take those, the pyron structures, they couldn't, if you try to organize those groups, it's nothing but only carbon, hydrogen, and oxygen, a hydroxyl group and hydrogen group, and hydrogen, and carbon. So you can confirm this one into 2 forms. One either could be shaped, it's like a chair, or it's a boat. All right? So now, out of those, only one is going to survive, not the other one. Which one is going to survive? Why?
More stable.
It's more stable because there are the bulky substitutions. Here, the substitutions will be there because these angles are already fixed. You cannot play around with those. Only thing, the substitution, the axial substitution, the way it is, that it is going to put less stress on the molecule. And if you put the bolt, it will sink that because it puts pull it down. The structure will collapse. So now we are clear up to this stage. All right. I don't think. I mean, it is behind the back what's happening. Not necessarily that people will be asking a lot of questions related to that, but it's important for us to build that to go to the next phase to understand that. So now the glucose we talked about, and there are various other sugars present, other derivatives. Here is the glucose family, beta-glucose. It could be phosphorylated, and that there could be amino sugars. The hydroxyl will be replaced by the amino group, or it could be acylated. The name will change. Here is the muramic acid, mostly you'll find in bacteria, but we have in our systems a 9-carbon sugar is the N-acetylmuraminic acid, which is the manosamine, phosphonol pyruvate, and the glucose and the manosamine to phosphonol pyruvate. That's what happened. Now you also have the galactose to galactosamine. The hydroxyl group will be replaced with the amino group. And the manosamine is what, remember the structure to show that. There are also deoxysugars. It could be not only the glucose, deoxyglucose is also present, but also we can have the deoxyribose and ribose, right? The deoxy, which means the hydroxyl group is replaced by the hydrogen atom. Yeah, here I made some corrections. The green arrow shows that the problem is the alpha, this is remember the alpha rhamnose, it has to be here. And this structure should be here. So that's the only corrections I made because I thought it's very important to do that. Then you have other acidic sugars, N-acetylmuramic acid or cyanic acid. Oh, sorry, this is muramic acid. Muramic acid and N-acetylmuramic acid. This is in bacteria. Bacterial cell wall is necessary for that. And in our system, the cell membranes, glycosphingolipids, which are components of cellular membranes, and many of the glycoproteins, which will be secretory proteins, so there are various functions attached to that. You will have a cyanic acid. Now, the glucose molecule can be oxidized. It could have a glucuronic acid. It 6 carbon, CH2H group is oxidized, or it could be a gluconate, which is the 1 carbon oxidized, the first carbon, CHOH, right? CHO, aldehyde group. Or it can be both, with the 6 carbon, the CH2OH, or 1 carbon, the CHO carbon. That both of them will be oxidized, and that name would be glucuric acid. But these molecules are extremely important for us. They do a lot of important, essential, but a dirty job. Because in our systems, we like the steroids, many of the lipids and things like the many drugs, they're metabolized, but sometimes they become insoluble. If they're insoluble, you cannot get rid of them, and if it's accumulating, it will have other pathophysiological situations. So the glucuronic acid will come for our rescue, it will conjugate with that, and making it a soluble product and be excluded from the system. Now the gluconate, that if you go to, I'm not particularly you individually, but I'm saying the people who get into the hospital, emergency room, first thing they put an IV, right? And then the salt solution goes in. And if somebody needed a calcium, how do we going to pump the calcium in? It's not in calcium chloride, because that will kill the cells, because it's all depolarized or hyperpolarized. So the calcium could be, because there's a chloride positive and negative charge, so they use the gluconate. Even this could be a negatively charged, it's not that powerful as the chloride is. So they will form in the form of calcium gluconate, and the calcium gluconate can be injected or given the IV to the system. So now you can see that it will build, not only we're trying to extract the energy, but it also can have a lot of peripheral functions in that. Interestingly enough, that you don't have to, if you don't, because sometimes they have come up with the 3-letter code for each sugars. The glucose is GLC, galactose is GAL, mannose is man, and glucosamine, galactosamine would be N, and glucosamine would be the GLCN. So these are 3 letters, because otherwise you don't have to write the whole name at the same time. But be careful to remember those 3-letter code, because sometimes they might not expand when you're in an exam. Thinking that, oh, we already discussed that, but not necessarily. We're trying to do it on purpose. But occasionally, since we are always used to do this kind of 3-letter code, we do this. So that way, so you get better, be careful and try to recognize those. Because you know that when the structures are being built, they will be using a similar, these codes. So now talking about the disaccharide, how many people have access to a computer? You did not have a computer, right? You have, everybody has it? Okay, get it connected to the internet. Because I'm going to do an exercise. Sorry, I should have told you before. Well, while we're getting ready, but let's disaccharide means 2 sugars. And the one, this is the exercise you're going to do it, because I'm going to ask you these questions. If you know that how many disaccharide structures possible when 2 amino acids are joined together equivalently, what will be your answer? 2 amino acids you're joining together. How many peptides, dipeptides will make? Or it will make from 2 amino acids? Only 1, right? Let's see the answer. The answer is 1. Okay, so the second one is this. So when you have internet, this is the tool you use. So talking about the same thing, the 2 glucose molecules, when they join together, how many structures are we going to get? https socratic.org, the biology, molecular biology, basics, carbohydrates. I hope it's working that way, because I had a different format. So you're taking the picture, or we're going to play around? So I'm saying that no, you have to get the number. You have to give me the answer. It's not the picture. Yeah, get to the link.
It says that there are no videos yet for the topic.
I'm not asking for the video. It's not a video. It should give you the answer.
Oh, the answer, okay.
No, this is not the answer. Is exactly what doing this?
Yeah.
Yes, sir.
HTTPS to here? The whole thing?
Biology slash molecular slash biology dash basics slash.
Carbohydrates?
Yes.
I don't know why it's not doing. I don't know. Okay. No, you have to ask. Did you ask? You have to generate a question. Yeah, you have to ask a question. Yeah. Yeah, that's a side. You have to ask this question. How many disaccharide structures are possible when two, it's a D, glucopyranoside are joined covalently? That's the question you have to ask to Mr.
So we
Google.
write it in here.
Yeah, you have to search, it's not going to, this is the link. That link will allow you to get the answer. But you have to raise the question, what your question is. When you do an internet for the mix, you say, okay, I'm mixing that with another. Say what it is. How many people got the answer? How many? 19. How many? How many of you got it, got the number? Then we're saying that what will be the number? Not everybody. Yeah, you got it, you got it, you got it, right? Okay. Anyway, so this is an exercise. I don't want to spend too much time on that because what the idea is that when you join two glucose molecules, you see the structures. How many structures, how many possible disaccharides you can generate? There are 19. So not necessarily all of them will be compatible, biocompatible, means we are going to use them or we are going to metabolize all of them. Some of them we do, not necessarily all of them. But then the question is, there will be a selective process, there will be some processes, that the selection will be allowing us to keep certain type of structure. The others, I don't know whether it's not being built or they've been destroyed, I have got no answer to that. But that's what example is that. So now it's only 2 sugars, now we make 3, 4, 5, 6, and then hundreds of them. So then how many different structures possible? But only one, only 2 structures. I mean, depends on maybe we said 1, maybe 2, maybe 3 will be biocompatible. Okay? So yeah, I don't have the answer. I didn't write down the answer just on purpose. Okay, so here's the example. Now we're talking about the 2 disaccharides building the glucose to 2 molecular glucose. So the alpha glucose and the molecular beta D glucose. Okay, that's coming from here. This is maltose. This could be both ways. Let's see. Here's the alpha glucose, beta D glucose, right? And as you mentioned there, that they do form a disaccharide. It could be condensation reactions because we're going downward here, and they're building the maltose, which just means alpha D glucopyronosine 1,4 beta D glucopyranose. This is the name of the maltose. Interestingly enough, when they describe that how it is in everything, all the information is here. What are the sugars present? What type of anomeric configuration they are, and what are the linkages involved? Which carbon is attached to which carbon? It's 1,4. So carbon 1 of this glucose is carbon 4. Now, this is alpha link, because remember it's the bottom, not the top. On the other hand, if you come to lactose, which is a galactose and a glucose, you are joining them together. Well, this is the condensation, you can do the hydrolysis, you can get back to single sugars. You can do it enzymatically, you can do it chemically. You put you can boil some acid, you can boil it, and then we'll dissociate and break the bonds. So the lactose is it's a disaccharide between galactose and glucose. So when it's joined together, to tell you that it's a beta D galactopyranopyranosine, okay, which is a pyranose form. It's the beta linkage here, and between 1,4, carbon 1 of galactose and carbon 4 of glucose, D-glucose. That's what we say, the gal beta 1,4 glucose. That's what it goes here. Now sucrose will be the glucose and fructose. It also tells you the group alpha 1, 2, alpha and 2 beta fructose here. And this is the trehalose, which is the glucose 1, 1. Now you can see that the glucose, if it is linked 1 to 4, it becomes maltose. If it's linked 1 to 1, talking the carbon, one carbon to other carbon, it becomes trehalose. Now, since a disaccharide, monosaccharides are reducing sugars, right? Now, when the disaccharides, two sugars have been joined and disaccharides form, some disaccharides could be reducing sugar, some of them are not. Now, looking at these structures, number of structures you have, can you tell me which one is not a reducing disaccharide? Remember the ring, not the ring, the open ring structure, the glucose starting, that numbering starts from 1, which is the aldehyde group. Carbon 1 is the reducing group. So if the carbon 1 is being used for the linkage formation, it's not accessible. So therefore, in trehalose is glucose 1,1. So neither this one nor that one is accessible or available. So this is not reducing sugar. But the rest of them are partly. Okay, this is available. So that way it can maintain its physicochemical properties. So here's the summary. It says the compounds with aldehydes of ketone groups, monosaccharides have several chiral carbons. Therefore, exists a variety of stereochemical forms. Bioquim we already discussed. Monosaccharides, which we discussed, are forming the N-acetyl hemicapital, and then the transacetyl alpha, the beta configurations, which are interconvertible. That's the mutual rotations we're talking about. Somewhere in the 10th slide. But it will come to, at one point, it will not move anymore. Then hydroxyl group of 1 carboxyl monosaccharide can add to an aromatic carbon of a second monosaccharide to form an acetyl. This is the glycosidic bond protects the aromatic carbon from oxidation. So there's another property there. The oligosaccharides, the short polymers, short chains, the monosaccharides bound by glycosidic bonds, and the common nomenclatures of the disaccharides will specify that at each anomeric carbon and carbon atom symbol is glycosidic linkage. So the number of sugar molecules you're adding is changing its size. So we're going to move a little bit faster to the other areas. Homopolysaccharides and heteropolysaccharides. So what are those? It gives you an idea. This is the kind of a homopolysaccharide. This is a straight chain compound, and this is the branching. And we'll see some of those polymers we have branching, some of them are straight. And these are heteropolysaccharides. You can see the different sugars. Now, when it comes to the heteropolysaccharides, there are a variety of things. In a sense, sometimes they're repeating disaccharide units X number of times, or sometimes it has a different sugars present. So depending upon the molecule. Okay, so here, homopolysaccharides, a couple of examples. It's a starch. Starches is from the granules. You can see this is the amylose structures. It's the alpha 1,4 linked glucose molecules. You can see it. And they're very dense. So many glucose molecules are packed that these are electron micrographs, so that they're electron dense. You can look at the structures under electron microscope. And these are the equivalent one. This is the starch is present in what? Where? In plants. The equivalent type of structures, equivalent structures is called the glycogen present in animal system, including humans, called the glycogen. So glycogens, there also you can see all these dots. There's so many glycogens. That's when the glucose molecules are packed in the form of glycogen, because it can pack many glucose molecules in one glycogen molecule. And at the same time, it's not going to increase. Molecular mass is huge, but it's not going to occupy too much space. Because when the glucose gets into the cell, it takes water with that. It's osmotic. And cell only can accommodate a little bit, right? But when in the same, if we call it 10,000 or 100,000 of glucose molecules packed in the form of glycogen, its molecular weight, molecular concentration would probably 0.0001 molar or something like that. So that can take a very little amount of water, and it can be present in the cell. So that's what it shows here. So now, what's the difference between the amylose and the amylopectin or glycogen? This starch is alpha 1,4, straight chain, no problem. But if there's a branching takes place, and the same thing happens in glycogen, but they're all alpha-1,4 link polymer, and the branching is at alpha-1,6. It's the sixth position of the sugar. Then another branching starts, and will continue with that. And that way they can build this type of structure. I think let me see, I may have it better. Yeah, I'll do it in a second. So this can be, this is the amylose. The blue one says that this is the reducing end and amylopectin. Now, what is the reason and what's the beauty of building the structure this way? Because when you come across, when the glycogen will be attacked to release glucose molecules, because that's the storage form, and the enzyme can take out only one glucose at a time. So that it will have two options. Either it can go from here, from the reducing end, or it can attack from the non-reducing end. So if you attack the reducing end, it's very, very, very slow, one glucose at a time. But if it comes from the non-reducing end, in one particular enzyme, in one shot, it can cleave out 5, 6, 7 hundreds of glucose molecules. So always it will be attacking for the non-reducing end. And that's why the structure has been built in such a way so that, because when there's a need, it cannot wait for too long. Not minutes, not hours, and not days. It needs to, like so for example, if you have to run, you got scared for something, you have to run, right? Your muscle has to be functional. And that muscle, the enzyme has to be released, in the sense has to be, it has to provide the enzyme. Enzyme has to come, the energy has to come from the glucose molecule. The glycogen has to be broken down, and the glucose has to be metabolized, and then you get ATP, so that the muscle will contract and then it will down faster. So that's what happens. And that's the biology of it, essentially. Now, in other systems, in insects and others, it's called the chitin. It's a something like it's a polymer of N-acetyl glucosamine. But the chitin is also present in the shell of this fish we have. The crabs, the shrimp, is also made up of chitin. And then the other one is in the plants, which you have the cellulose. It's the same thing, it's a polymer of glucose, but we cannot digest cellulose. Why? What's the problem? What's the difference between cellulose and glycogen or starch? Yeah.
We don't have
Sorry, go ahead.
we don't have the enzyme to break the specific bond
Why?
that cellulose have.
Why not? I mean, what enzyme it needs? And what exactly is going to be breaking down? What bond is going to break down?
The 1,6.
1,6. Okay, ¿qué más? Again, anybody else? Everything is on the screen. Nothing hidden. Hmm?
It's beta, not alpha.
Say it loud.
It's beta, not alpha.
Beta what?
1,4.
Beta 1,4. In starch is alpha 1,4. In glycogen, alpha 1,4, right? And then alpha 1,6. There is no beta. Since the glucose is joined together through the beta linkage, beta 1,4, beta linkage, so we don't have the enzyme to break down those bonds, because the cellulase, which you need, the bacteria of the ruins of the cows or the animals, they have that. We don't have that enzyme. So that's why we cannot digest it. But cellulose is a beta 1,4 linked glucose, nothing more, nothing less. Okay. Let's see what happens. And also because of this, then it gives you, as you know, the different protein structures, they do that, and carbohydrates also do the same thing. The beta 1,4 link gives you the straight structure, straight line structure. The parallel structures gives. And obviously there are some, these are neutral molecules, and there are van der Waals forces, hydrogen bonding, everything is possible. But when the glucose is linked by the alpha 1,4, it gives the coil-like structures. The structural components completely change. Now, if you take I don't think the starch has a fiber, but you can take an example of the starch, or maybe rice. When the rice is cooked, you can break it with it. So, but at the same time, but the cellulose, if we take a simple cellulose fiber, we try to, on the tree trunk, we try to get that and try to rip them up, try to break it.